Okie dokie. Let's get started with magnetism. So 3 sections for magnetism. 1, we'll talk about يعني ايه magnets اصلا, يعني what's a magnet, what's a magnetic field, and the magnetic field of magnets, and the magnetic field of an electric current, so wires and stuff. Second, we talk about electromagnetic induction, which is generating electricity using a magnetism. All right? And third, هنتكلم عن الموتور effect اللي هو when you pass a current through a wire, it experiences a force فالwire بتتحرك and it moves. Let's start with the basics الأول. As a friendly reminder again, please use these numbers as a checklist. Once you're done revising, read every sentence and make sure you understand what each sentence means. لو لقيت نفسك مش فاهم sentence فيهم, mark it, go back and revise, or go back and watch the video again, or ask me what does it mean in case you realize انت مش فاهم ايه بالظبط. ده الchecklist بتاع كامبريدج اللي بتبقى حطاه للريفيجن. بس let's just get started with us على طول بقى كده. So, what's a magnet? A magnet is a natural object that attracts and repels other magnets برضه. So a magnet attracts and repels other magnets. If you have a north pole, and it has 2 poles, north and south. So any magnet has 2 poles. North and north repel, south and south repel, north and south attract, exactly زي الcharges. So same relationship. Opposites attract, like repel. However, just like charges, there are certain materials that also get attracted, even though they're not magnets yet. And they are iron and steel. Now, في materials ثانية, to be honest. There's nickel, there's chrome, there's cobalt. Like, there are other materials that are magnetic. بس مش هناخدها في السيلبس بتاعنا. Like, ملناش دعوة بيها. We're just going to talk about iron and steel. Okay? So speaking of iron and steel are already magnetic. يعني هم أصلاً magnetic materials already. الفكرة بقى فيهم إيه؟ And when you put a piece of iron near a magnet, it becomes what we call magnetized. يعني هي بيحصل لها الأول magnetization. يعني بتبقى magnet. It gains some north and south. أو to be honest, بتrearrange north و south جوه. يعني an piece of iron has lots of north and south poles جواها, but they're all messed up. لما نقربها من magnet, all of these north and south poles arrange themselves and align, فبيبقى عندي a fixed north and a fixed south pole. This action of a magnet arranging magnetic poles جوه a piece of iron is called induced magnetism. Induced magnetism. كلمة induced يعني introduced or دخلت في حاجة. وهنستخدم كلمة induction أو induced دي كذا مرة النهاردة. Talk about that a lot. بس المهم, when you put a piece of iron next to a magnet, it gets magnetized and then it gets attracted. بصوا الترتيب الأول. You put it close, it gets magnetized, and then it sticks. Pull the iron away من المagnet and it demagnetizes. In other words, it becomes temporarily magnetized بس لما تبقى جنب المagnet. Pull it far away, it loses its magnetism. We call iron a soft magnetic material. طب steel بقى. Steel, if you haven't noticed, or if you don't remember from chemistry, is an alloy of iron. It's iron and carbon together. Iron and carbon بتحطوا مع بعض. But when you bring, it's already magnetic برضه. So when you bring steel next to a magnet, it also gets magnetized. زي iron بالظبط. Actually, it's a bit weaker than iron. عشان impurities, it's not pure iron. But when you pull it away, it stays magnetized. This is because steel is a hard magnetic substance. It is difficult to magnetize and difficult to demagnetize. صعب قوي ان اخليها magnetize. مش صعب قوي. غلط كلمة قوي. صعب بس. So you move it close. It magnetizes slowly, but it does not demagnetize, or it demagnetizes very slowly. فأحسن حاجة أعمل بيها a permanent magnet would be steel. Whereas if I want something temporarily magnetized, we use iron. Is this used in a circuit breaker? لا. Like we don't use steel in a circuit breaker. We use iron. وهنشوف ليه بعد شوية. Like in a bit هنشوف. Now, just like charges in electricity كان عندها an electric field. Magnets have what we call a magnetic field, which is defined as nothing more than a region where magnets experience a force. And it follows the same rule as charges. ليها direction. So in charges, the field was from positive to negative. The space between the lines can be Orrini field strength. The closer the lines are together, the stronger the field. The farther away the lines are, the weaker the field. But in a magnetic field, the field is always from north to south. It is always from north to south. إشمعنى الfield from north to south? Like there has to be a reason. That's because الfield بتاع magnetic field shows me the direction that a compass would point in if it was placed في الفيلد ده. Okay, so a compass needle للي ما يعرفش تعالوا نراجع. A compass needle is actually a magnet. The needle of a compass is actually a magnet. This end of it is the north and the back end is south. So it's a compass, it's a magnet, sorry, on a pivot. فلما اجي اقربها من sorry, I just have this habit. لما اجي اقربها من a magnet, it also gets attracted and repelled. In north هي repel in north, it points away from the north, and north بيبقى towards the south, it points towards the south. So the direction of a magnetic field shows you the direction of a compass needle in that field or in that space. زي ما انتم شايفين space ما بين lines عند poles is very small, whereas here it's much larger. يعني the field here is very strong and the field here is very weak. If you put two poles next to each other زي parallel plates بالظبط, the field lines are now parallel and equidistant, which means the field strength is uniform or constant. So far, so good. One of the things you need to be able to describe is an experiment that we use to determine the direction and shape of a magnetic field. Here's how we do it, and here's how to describe it. You take a compass and put it next to the magnet, next to one of the poles of the magnet, and mark a point on the sheet of paper اللي انت هتحط عليها المagnet والcompass ده. Then take that compass وحطها on the other end of that point. You'll find the needle pointing in a different direction. Make a mark. Put it here. 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 Make a mark. I'm sure you're bored of me saying make a mark. بس يلا. Okay. ماشي يا أحمد. And then draw a line through these marks and you'll see the field line. Do this several times around a magnet and you'll draw the magnetic field lines that we've drawn. فتاني, put a compass in front of the magnet or just around the magnet and check the direction of the needle and mark a point where it's pointing. Then move it to the other end of the point and make another mark. Repeat these steps several times and draw a line joining these marks. بس كده. Okay. Good. Now, this is the easy part. This is where we revise the old basics. يا مستر أنا عارف يعني إيه magnet north and south bit. Okay? Good. أمال بقى electricity. إيه علاقة electricity with magnetism? This is actually very important. Okay? إيه علاقة electricity with magnetism? Here's the funny thing. Magnets, okay? Magnets, or magnetism, to be honest, comes from electricity. The source of magnetism حتى جوه الiron والsteel جاي من electricity. Okay, let's see why. First, if you pass a current through a wire. A copper wire. تاني, this is going to be a copper wire. This wire is going to produce a magnetic field around it. وشكل المagnetic field عبارة عن concentric circles. يعني مش طالعة من north to south. It's just a bunch of circles with the wire in the center. The further away you move from the wire, the weaker the field. فالسبيس ما بين اللاينز, وخلينا نمسح بقى الشخبطة اللي انا عملتها هنا, والسبيس ما بين اللاينز بيزيد as you can see. طيب. So, but here's the thing. أنا لو قفلت الكرنت, like if there is no current, there will be no field. في حاجة مهمة لازم أقولها في اللانجوج بتاعتك وأنت بتستخدمها when you're answering questions. If I ask you, why is there a magnetic field? هتقولي because the current produces the magnetic field around the conductor. مش الكوندكتور هو السورس بتاع الفيلد, هي الكرنت which is the flow of charges. إن في charges positive أو negative بتتحرك, أي charge بيتحرك بيعمل حواليه magnetic field. Any charge بيعمل حواليه magnetic field. So please keep that in mind, okay? So a current flowing through a conductor اهو produces a circular concentric magnetic field around it, around the conductor. Okay? طيب. Very good. Now, الفيلد direction بقى ملوش north و south. It doesn't have a north pole and a south pole, but it does have a direction. It could be clockwise or it could be anti-clockwise. حسب ايه? The direction of the current. You have two directions. Either the current is up or out of the page, or the current is down or into the page. وقبل ما نكمل, please خدوا بالكم من حاجة. On any exam paper, you have 6 possible directions that you can refer to. Up أو top, down أو bottom, right or left. تقول لي مستر انت قلت 6. اقول لك or out of the 3-dimensionally بقى, or into. These are the 6 directions for any sheet of paper. خلاص? So up, down or top and bottom, right, left, out of or into the paper. So when I say out of or into the paper, I literally mean كأنك عملت ايه? جبت a sheet of paper and you poke it. This is out of the paper, عليك انت, and this is into the paper, down. تمام? So keep these directions in mind واحنا بنشتغل. طيب. The direction of the magnetic field is anti-clockwise if the current is out of the paper. And the direction of the magnetic field is clockwise if it's into the paper. عشان نفتكرها دي بطريقة أسهل شوية, we use what we call the right hand grip rule. وبصوا عليها دي جنب الايه؟ الرسمة اللي هنا. If the current is going up, that's my thumb, current is going up out of the page. بصوا على بقية ايديك وبتقفل ازاي. Look at the rest of your hand, بتقفل ازاي. Anti clockwise, like curves anti-clockwise. So up is anti-clockwise. وده فعلا اللي حصل هنا. So obviously if the current is down هتبقى ايه؟ Clockwise. So if the current is down or into the page يبقى clockwise. بس. طب. Instead of a straight wire, لو خدنا بقى الواير دي ولفيناها, like if I get any random wire, this from Xbox controller, if I take a wire and just turn it around my pen, لفيت, you end up producing what we call a coil. Okay, this is a coil. Or what we call a solenoid. So solenoid is just a wire that's coiled. Okay. Coil the wire connected to a supply, so a positive and negative side of a cell or a battery. The current will flow through وهيعمل magnetic field. This field will look exactly like a bar magnet. طالعة من ناحية وداخلة من الناحية التانية. With one difference. إن في field lines جوه الكويل. There are field lines inside the coil. برضه a magnet doesn't have a field inside. A coil does عشان it's no, it's just a coil. It's empty on the inside for now. The field will obviously move from north to a south. بس أنا إيش عرفني what the direction of the north and south poles are؟ عندنا برضو right hand rule. بس قبل ما أوريكم right hand نعمل إيه؟ Here's a short hint or like a quick dirty tip كده. The north pole of this coil هتبقى almost always where the negative side of the battery is. خلاص؟ But تقولي ماشي يا مستر I don't want a shortcut. أنا عايز ال actual rule أستخدمها. أجيبها إزاي؟ Step 1 draw the direction of the current in the coil. Especially الفرونت بتاع الكويل الوش بتاع الكويل. Look at this. It's going upwards كده. Turning going up. ولما بقول up قصدي up وبتلف ورا and then up بتلف ورا up بتلف ورا and then it's out. Your fingers في right hand rule هم الكويل. So hold your hand and make sure your fingernails بصة في نفس direction بتاع الكويل. So when your fingernails are pointing up and you close your hand, your thumb had point فين? To the left. Your thumb will point to the left. يبقى ده النورث. Your thumb is the A, north pole. Okay? Now, how do I make this field stronger? ثلاث حاجات. You increase the current or voltage, مش فارقة, but the current is what produces the field, so make it stronger. Increase the number of turns, يعني خليك عندك turns أكتر. Or using an iron core, يعني إيه؟ حط جوه الكويل ده a piece of iron. أو بمعنى أصح, get a piece of iron first and then coil the wire around it. طب أنا استفدت إيه طب when I put a piece of iron inside؟ يعني أنا استفدت إيه كده هنا؟ ها؟ What did I gain؟ إن المagnetic field بتاع الكويل, let's draw this in red. خلاص. The magnetic field of the coil is produced. It also magnetizes the iron. فده iron also becomes a magnet. فهو كمان بيطلع magnetic field. So how many fields do you get in the same space? اتنين. You get two fields. The magnetic field is a lot stronger just because you put a piece of iron. Okay? And this is what we call an electromagnet or a solenoid. Question. Why do you use iron and not steel? ليه بنستخدم iron ومش steel؟ عشان قلنا steel is a hard magnetic substance. It magnetizes, but it cannot or does not demagnetize very easily. Okay? It magnetizes and demagnetizes very hard. So it's not good for an electromagnet, because the advantage of an electromagnet, or solenoid, is you can switch it on and off. If you put steel, you can switch it on, but never off. Because you switch it off and there's no current, the core is still magnetized. Bad idea. Yeah. We've already seen one application of this, اللي هي ايه؟ خلاص, Rana, you've mentioned that اللي هي circuit breaker. We've talked about the circuit breaker last time for electricity. So one application of this is the circuit breaker. The second application is a relay. And what's a relay? A relay is a component that allows you to use a low voltage circuit or a low current circuit, like a 1-volt circuit, to switch on or off a high voltage circuit, like a 300-volt circuit. How? بصوا على setup ده. Here's a circuit, supply, switch, and this is the coil, solenoid, electromagnet, connected to a lamp. Lamp مش مهم. I just need this as an indicator. والله كنا ممكن نحط an LED and that would be better عشان يوريني if it's on or off, بس مش مهم. Look at the other side بقى. It's got the high voltage supply, this high voltage lamp, وحط مكان اللامp whatever device you want. You want your air conditioner, you want your deep freezer, you want your fridge, you want a washing machine, اللي انتوا عايزينه, whatever I want. He is always good. And an iron switch زي السيركت بريكر بالظبط. Go ahead, John. زي السيركت بريكر بالظبط. Exactly like it. فايه اللي بيحصل بقى؟ If you close this switch, this low voltage, low current circuit الغلبان ده هيعمل ايه؟ هيpass through the coil and it magnetizes. هيعمل ايه في iron switch? Attracts it and closes the circuit. Tuck. Moves and closes the circuit. And now the high voltage supply has a current going through, or like passes a current through the second circuit, واللمبة دي تنور تبقى زي الفل. And that's how it works. A low voltage supply or circuit can be used to turn on a high voltage or high current circuit. Best. And finally, speakers. That's one decent application. It's a very easy application. I currently have, earphones in my ear عشان أسمع نفسي to make sure إن feedback كويس. Or if I'm using it to listen to music, or if I'm using it to listen to a YouTube video or whatever. How does a speaker work? Earphones أو حتى regular speakers. Here's how they work. First, فيهم حتة كده اسمها الكون. من قدام, from the front, it kind of looks like this. It's just a circle with a little circle in the middle. This cone is like a sheet of paper. When it vibrates the air in front of it and around it, فبيعمل sound. فthe idea is ايه؟ أنا عايز ده vibrate فيعمل لي sound. ويطلع الميوزك or whatever it is أنا بسمعه. الكون ده بيبقى متوصل بفيكست magnet, a bar magnet. North, south, مش مهم شكل المagnet. بس around the magnet itself بيبقى فيه coil. يعني we get a coil كده. والكويل ده متوصل بالسيجنال بتاعتي اللي هو الكرنت اللي هي الميوزك. Remember عندنا السيجنال بقى could be DC, could be AC, it doesn't matter. Analog قصدي أو digital, could be anything. بس لما يدخل السيجنال ده الكرنت اللي بيدخل في الكويل بيعمل إيه؟ يعني the current that goes through this coil over here بيعمل magnetic field فبيبقى له north و south and it keeps changing فبيقعد يحرك ويأتراكت ويريبل the fixed magnet, the bar magnet, which is connected to what? The cone. فالكون يعمل إيه؟ vibrate back and forth. فتاني, you pass a signal or a current through the coil or solenoid, which attracts and repels the fixed magnet or the bar magnet that's connected to the cone. So the cone vibrates and vibrates the air molecules producing a sound. Okay. Let's solve a few questions. وهتشوفوا إن مفيش questions paper 4 حاططها لكم هنا. There's a magnet in the cone. Yes, there's a magnet stuck to the cone. حسب بقى the size of the earphones, if they're like small and tiny كده, ولا if it's a giant nice speaker, the size of that magnet changes. عشان كده speakers الكبيرة بتقدر تديني volume أعلى و amplitude أعلى. Because the magnet there is bigger, it's stronger, it can move a bigger distance, فبتعمل لي صوت أعلى. الماجنتس اللي هنا غلبانة صغنونة كده, they don't work very well. طيب. There aren't a lot of paper 4 questions for this topic because this topic is used to build up on the other topics اللي هناخدها اللي هي الاندكشن والموتور وكل حاجة. So نبدأ بقى الأول بجون 23 paper 2. This is all paper بقى 2 stuff. The magnetic field of a bar magnet can be represented by magnetic field lines. Which diagram shows two magnetic field lines correctly? بيطلع من النورث يدخل للساوث. So A. ده غلط, ده غلط, ده غلط. Clearly. طيب. Which row gives the metal used to make the core of an electromagnet and one property of the electromagnet? So electromagnet core قلنا بنستخدم ايه؟ Iron. Why? Because it's a good temporary magnet. You can switch it on and off. B is the correct answer. طيب. Next. The diagram shows the magnetic field around the solenoid carrying an electric current. بس هو مش موريني directions ولا أي حاجة. It's just, magnetic field, coil. What happens to the strength of the magnetic field and the distance between the lines when the current is increased? حلوة دي. The current is increased. The field is now stronger. فاحنا عايزين strength increases. And if the field is stronger, يعني في lines أكتر. The space between the lines is going to be smaller. C. صح يا رام. Excellent. Finally بقى. An unmagnetized piece of soft iron. على فكرة هو بيحب يستخدم كلمة soft iron a lot. Not because iron is soft كmaterial you can bend it ولا حاجة. لا. It's called soft عشان it's easy to magnetize and easy to demagnetize. Okay. Soft iron is placed close to a strong permanent magnet. Okay. What is the induced polarity of the end X? يعني what is the pole of X? حاضر هرجع للسؤال اللي قبله. Of the soft iron. And in which direction does the magnetic force act on the soft iron? طب دي سهلة. If this is north, X ده هيبقى south. So I want C or D. Then, obviously it's iron and a magnet فيحصل attraction. So it moves to the left. So the direction of the force on the iron is to the left. But the answer is C. Okay? Lion asks, why is it not B instead of C? Do you mean question 29 here? Yeah. What did he say? The current is increased, صح? If you increase the current, like we said earlier, one of the three things you can do to increase the strength, one of the things that you can do to increase the strength is what? Increasing the current. Is to increase the current. So if you increase the current, the strength of the field increases. فحلو. It's either C or D. غصبا عني. طب second question, what happens to the distance between the field lines? We said the closer the lines are to each other, the stronger the field. And the farther away the lines are from each other, the weaker the field. But didn't we just say in the strength بتاع magnetic field Z, it increased? يبقى distance between the lines will decrease عشان يبقى field stronger. Okay, Diane? Okay, you're welcome. We haven't reached the spot. Lenz's law. No. Lenz's law won't be applied here. هناخد Lenz's law كمان شوية دلوقتي حل في induction. Okay. Why is the force to the left? Because it gets attracted. مش iron permanent magnet will attract. But he's not asking about the magnet. What's he asking about في السؤال ده? Which direction does the magnetic force act on the soft iron? يعني مالكش دعوة بالمagnet. iron هيمشي ازاي? To the هيروح للمagnet. So to the left. بس. So it's a matter of the language of the question. Next. Okay. Electromagnetic induction. Arguably the most important chapter في magnetism. ليه؟ Most of the questions اللي بتيجي في paper 4 بتبقى عن induction. So what is induction? طبعا we'll describe two applications of induction, the generator and the transformer. First, what is induction? Simply put, لو أنا جبت wire, I'm the one who got a nice copper wire كده, and I connected the wire to a voltmeter. In other words, مفيش current في wire, not yet. يعني أنا ما دخلتلوش electricity, okay? مفيش current. If you grab the wire and you start moving it up or down, it will generate electricity. If you stop moving, it will not generate electricity. If I ask you to demonstrate this, هنعمل إيه؟ هنقول له كده. Connect the wire to a voltmeter and move it between the poles of a magnet. هنشوف reading on the voltmeter. بس مش لازم الواير بس اللي تتحرك. Like the wire moving is not the only thing that could happen. the magnet could move. هو important thing is ايه؟ ان as the wire move, this is a cross section of the wire, لازم الواير وهي بتموف to cut through the magnetic field lines. So when it does cut through the magnetic field lines, it generate electricity. Every time it cuts through a line, cuts through a line, cuts through a line, it generates a current that flows through. خلاص? Or instead of the wire moving up and down, I can move the magnet up and down. Or better yet, خدوا المagnet and move it in and out. Move it in and out of the solenoid or the coil. فالمagnetic field بتاع المagnet هو اللي هيعمل ايه؟ cut through the coil بتاع الكويلز بتاعت السولenoid. And if you connect it to a voltmeter, generate electricity and you'll see a reading. الإفكت ده اسمه electromagnetic induction, which is what? The induction, or كلمة induction هنا could mean the generating, right? The generation of EMF, voltage يعني, in a conductor moving across or moving through a magnetic field. خلاص? So again, what is electromagnetic induction? When you move a conductor through a magnetic field, it cuts through the field lines and generates electricity. اتفقنا؟ طب. The magnitude of the EMF, يعني the voltage that you generate, can be increased by doing one of three things, or all three things that I see. Since it's the motion that generates, Since it's the motion that generates the electricity, moving the wire faster generates more, a higher voltage, فحلو. Or using a stronger magnet, that would increase the voltage generated, because a stronger magnet معناه في more field lines, and if there are more field lines, there's more cutting, and if there's more cutting, there's more induction. وآخر حاجة, increasing the number of turns of the coil. يعني نلف الكويل أكتر، عدد لفات إيه؟ أكتر. Okay? طيب. So that's how we generate more or less electricity. بس بقول لكم إيه بقى؟ A very important detail. A very important detail with the cutting part. مش أي motion generate electricity وخلاص. Because if you grab the wire and you move it down through the field of these two poles or up, generate electricity, no problem. But if you move the wire right or left, generate 0 volts. ليه؟ علشان لما magnetic field يبقى parallel للdirection of motion of the wire, there's no cutting that's happening. There's no change in the magnetic field lines that's happening. خلاص مفيش change in the magnetic field lines اللي بتحصل. خلاص. And because there's no change in the magnetic field, ايه اللي بيحصل؟ You do not generate electricity. Only when you cut through the field lines, you generate electricity. Which is why you make the maximum generated voltage لما تقطع الفيلد lines perpendicular كده. And you generate 0 in your parallel. فطبعا if you move it كده بangle, this takes more time and a larger distance to cut the same field lines. يعني عشان امشي من هنا لهنا vertically مش زي هنا لهنا at an angle. So you generate less voltage. يعني مثلا لو ده 100 volts وطبعا ده 0, يبقى if you're at 45 degrees you should roughly get a 50 volts. كل ما نبقى perpendicular أكتر you get more voltage. كل ما نبقى parallel أكتر you get less voltage. تمام؟ Now, the amount of voltage زي ما قلنا كده بيعتمد على إيه؟ The speed, the strength of the magnet, and the number of coils, and the angle. But if I move the magnet down and then up and then down and then up, هنلاقي النيدل بتاعت الفولتميتر تديني reading positive بعد كده negative, positive بعد كده negative, positive بعد كده negative. It's not making up its mind. It's changing. It's alternating. ها؟ طب ليه بقى؟ Because the direction of motion of the wire affect the direction of the current that you generate. And this is determined by two rules أو laws. حاجة هنسميها Lenz's law. مش لازم تحفظوا الاسم، بس مهم الديفينيشن اللي فيها، اللي هي الستيتمنت دي هنقولها دلوقتي. Fleming's right hand rule. So the magnetism كلها hand rules. طيب, how do you use the right hand rule? Let's use the right hand rule first, and we'll use it here because according to this diagram أنا بقول if you move the wire up, the current هيtravel from, I'm going to call these ends A and B. The current هيtravel from B to A. If you move the wire down, the current هيtravel from A to B. إيش عرفني؟ Here's your right hand. اعملوا right hand كده. Okay? It's like holding a gun. Bam, bam, bam. I shot you down. خلاص. But your middle finger is perpendicular to your index finger. Well, thumb is perpendicular برضه to the index finger. يعني لازم تشوفوا حرف L no matter what direction you look at your hands. خلاص. Not because you lost or anything, but because L is just a 90-degree line. So many L's here. So هنتكلم على left or right. For now, it's right. ماشي? We're generating electricity, okay? So it's right. There's another version called the left hand برضو. Gangster science بقى كده. بس في الحتة اللي بعديها على طول. في الموتور. بس في الجنريتور نستخدم right hand. يلا. Here's how. وطبعا يا جماعة أنا عارف إن أنا فنان. فلو سمحتوا استحملوا. First, right hand, your index finger هي المagnetic field. بصوا بقى على الرولز. Your index finger هي المagnetic field. Your middle finger is the current. Your thumb هي ال direction of motion اللي انتوا بتحرك فيها الواير. We know the direction of the field and we know the direction of motion. احنا عايزين نفايند ال current. لو رجعنا بقى للرسمة فوق تاني اهي. The magnetic field is from north to south. فماي index finger هتشاور يمين. Okay. My thumb is going to point upwards. خلاص عشان we've moved it upwards. Your middle finger is going to point كده غصب عني. That's how my finger will stand. And here's the rest of your hand. So I know your hand looks amazing في الصورة دي, but this is how your hand should be. Magnetic field from north to south, يعني pointing to the right. Your thumb points up, so your middle finger is into the page or, up the wire. So the current is moving كده. طب, what do you think will happen if I reverse the direction of motion? حركت الواير لتحت. So your index finger هتشاور يمين برضو because that's the magnetic field من north to the south. The force is down, or the direction of motion is down. So your middle finger is pointing out of the page. You can't see it because it's pointing towards me. It's towards me. It's towards my mouth. If you move the wire down, the current هيبقى out of the page. Again. If this is the north and this is the south, and you decide to move the wire down instead of up, the current will be from A to B, out of the page. إيديا هتبقى شكلها كده. That middle finger is wonky, بس يلا. Your hand is like upside down, and here's your middle finger out of the page. كده. And the current هنا is into. بس. في fingernails هنا عشان بس يبقى باين. And there you have it. Now, honestly مش هنستخدم right hand rule a lot. We're not going to use the right hand rule a lot, okay? But there is another type of rule or law that explains why the current is generated in this direction. And it's called Lenz's law. What's Lenz's law? Also, I'll statement. The direction of the induced EMF opposes the change causing it. قصدي إن when you move this wire down, I grab this wire and moved it down, the current is generated in order to resist your motion. Okay? This is most evident فين؟ في الcoil أو solenoid, because when you move the magnet into, this is very easy to understand في solenoid, when you move the magnet into or towards the coil, مش احنا كده هنgenerate electricity? We're going to generate electricity in the coil. Do you all agree? هيبقى في current ماشي في coil. Yes? قولوا لي yes. That's what I want. I want to hear a yes or see a yes. هل في current? Yes. But here's the thing. مش احنا برضو قلنا من شوية ان when there is a current في السولينويد او في الكويل، بصوا ارجعوا لورا when there is a current in the solenoid or the coil has a magnetic field. Yes ولا لا؟ when there's a current in the coil, is there a magnetic field? Yes برضو. Here's the problem. Oops, sorry. Please don't get busy. There we go. You move the magnet towards it, the North Pole. This generated the current. Oops, the current we generated also produced a magnetic field. The magnetic field will have a north and south pole. يعني the coil will now have its own north and south pole. دايما the direction of the current induced هيبقى opposing the change causing it. انت بتقرب magnet, the solenoid will generate a current and a magnetic field to go like, nah, repel. I don't want you. So the two fields interact and try to repel. But here's the thing. This is a toxic relationship. ايه ده قصدك ايه toxic relationship؟ ايه علاقة relationships بكده؟ If you grab this magnet and try to move it away, يعني it's in the coil خلاص and you're moving it out away, this will also generate a current. It's because you move the magnet in the opposite direction. الcurrent هيمove in the opposite direction. فالمagnetic field هيبقى in the opposite direction. ده هيبقى south, ده هيبقى north. هو wait a second. لو ده south وده north اهو هيحاولوا يعملوا ايه؟ attraction. If you're trying to move the magnet away from the coil, it goes like, no, don't go. ويحاول attract you back. If you move the magnet towards the coil, it goes like, no, I don't want you. It repels. And it's a very toxic relationship. تقرب بيحاول يبعدك، بتبعد بيحاول يقرب منك تاني. Tries to attract you again. narcissistic magnet, yes. A lot of questions بتحب الحركة دي اللي هي it goes like, hey, you don't know what the poles here of the solenoid are. Okay? انت متعرفش. We are moving the north pole of a magnet towards it. Identify the poles of the solenoid. المagnetic poles بتاعت السولينويد دي. فطالما بنقرب north، ده north وده south. يعني لازم دول يبقوا opposite, as in they repel each other. لا, you've decided to pull it away. ايه اللي هيحصل؟ لا, ده هيبقى south ده هيبقى north. جت قبل كده في multiple choice questions. خلاص؟ keep this in mind. It's very common في multiple choice and occasionally في written questions. Lenz's law. He will never ask you to define, hey, what is Lenz's law? But he will often ask you, describe the direction of the induced current or describe why the current was induced in this direction. هتقول له because the direction of the induced current or the induced EMF opposes the change causing it. بس. طيب. ممكن بقى ناخد الحركة دي بتاعت الاندكشن وبليز باي ذا واي memorize this term. كلمة induction نفسها is a point of questioning. يعني the term itself is a point of questioning. يسألك what's the name of the effect where we generate electricity when a conductor moves through a wire? Electromagnetic induction. You have to memorize the name. We have two applications بقى. The generator. Oops. The generator and the transformer. What's the generator? The generator is a device that generates electricity by converting kinetic energy to electric energy. هتفكر كده شوية تقول ايه ده يا مستر wait a second احنا شفنا كلمة generator دي قبل كده فين؟ go back in time كده يا مستر احنا خدنا unit 4 part 1 لا unit 3 part 2 1 لا unit 2 لا unit 1 فاكرين لما اتكلمنا على energy generating electricity كان في الباور ستيشنز في اخر كل الباور ستيشنز كان في ايه توربين وجنريتور كان التوربين لما بيلف عشان حاجه بتخبطه wind water steam كان بيلف حاجه اسمها الجنريتور والجنريتور بيجنريت electricity and here's how it works literally you get a coil which is just a wire a copper wire ادي coil اهو and we pivot it in the center بنحط لها pivot وبنوصل الكويل ده بالتوربين بتاعنا فلما الويند او الواتر او الستيم يخبطوا like when wind water steam hits the turbine it turns فهتturn مين the coil فلما الوايرز دي ودي بتوع الكويل they move up and down what do they do what do these wires do if you look at their cross section they move up they move down they cut through the magnetic field inducing an EMF and they generate electricity. So just by turning a coil inside the magnetic field, بنلف الcoil in a magnetic field, that be cut through the wires, we generate electricity. That's basically it. Now, we only have one problem. The problem is إن أنا لو وصلت wires directly على الcoil والcoil ده بيلف and it rotates هتاخد الوايرز دي وتلفها على بعض. Bad idea because الوايرز هتتقطع. Like they'll get torn apart. فinstead بنعمل ايه بقى؟ بنعمل ايه؟ بنوصلها with two carbon brushes and a slip ring or two slip rings. الكويل ده literally ملحوم and it's welded onto the first ring. والكويل التاني اهو is going through the other end is welded to the second ring. So when the entire coil spins لما ده كله يروتيت الرينج ده بيروتيت والرينج ده بيروتيت and they're touching something called the carbon brush. These carbon brushes do not move. They can conduct electricity but they do not move. فthey بس just rub on the surface of the brush. فلما بنجنرate electricity في الكويل let's say في current جاي كده it goes through the ring and out of the brush تشغل لي light bulb for example and then the current goes back through the brush and out to the other end of the coil ويدخل generate electricity and you have a circuit. If I ask you what's the function of the slip rings and carbon brush, it is to do what? To conduct electricity to the circuit without twisting or breaking the wires. That's it. How do we increase the voltage that we generate? Rotate it faster, use a stronger magnet, increase the number of turns of the coil. And instead of one loop, you can use 2 loops, you can use 3 loops, you can use 4 loops, 5 loops, 10 loops, 157 loops. طبعا ما نوصلش 157 ممكن نوصل ل thousands بس ايه that's up to how much space we have to coil the wire. yeah. طبعا ليه الالكتريستي اللي بتبقى generated بقى من الجنريتور AC. Okay, slip rings ensure the current goes through external circuit. That's exactly what we said. It allows the current to go through the circuit, the output circuit, without breaking the wires. Yes, because you can connect wires directly as على الcoil, but you won't be able to keep that up for long because هتاخد الwires دي وتلفها على بعض. So we need something that both rotates and stays still at the same time. يعني we want the output circuit تبقى stationary من غير ما تلف and the coil needs to be able to spin freely. Okay. Why is the current بقى alternating? Well, simple. عشان حاجتين. First, الكويل وهو بيلف, when the coil rotates. When the coil rotates, ايه اللي بيحصل بقى? The wire that does the cutting, for half of the time, it goes up the magnetic field. So you get a direction. And then the other half, it goes down. So you get the opposite direction. Okay, so you get the opposite direction of the current. فكل شوية تلاقي الكرنت أو الفولتج positive ونيجاتيف, positive ونيجاتيف, positive ونيجاتيف. And second, why is the value not constant? زي ما قلنا, the angle affects the voltage that you generate. لما الكويل يبقى horizontal كده, these two ends are moving up and down. يعني بيقطعوا perpendicular to the field. They're moving perpendicular to the field. فده بيجنرate maximum voltage. وبعد كده وهي بتلف بتبقى بانجل, وبعد كده لما بتلف بتبقى parallel. Oh, wait a second. If the wire right now is moving parallel to the field, you generate 0 volts. You generate 0 volts لما الكويل يبقى vertical, أو لما الends بتاعت الواير دي تبقى parallel للفيلد. You generate the maximum voltage بس لما الكويل يبقى horizontal. And the coil is horizontal because the wires are moving perpendicular to the field. تمام؟ Okay, here's the question. What's the purpose of the carbon brush? The carbon brush and the rings together conduct electricity without the circuit breaking. عشان خد بالك من حاجة هنا. Like, hold on, let me erase this. I don't think an eraser would work, صح? لا, it would work. خد بالك من حاجة. This ring is spinning. It's rotating. The brush, however, that's connected to your voltmeter outside is not supposed to spin. فإيه الحل؟ إحنا بنثبت ده. This stays put in place. This does not move. Yes. But it's touching the brush. Sorry, the brush is touching the ring or the split ring, the slip ring. So when the ring spins, إيه اللي بيحصل? It's like a wheel that's spinning that's rubbing on a flat surface. فده بيضمن إيه؟ إن the wheel that's spinning can move, it can spin and rotate براحتها, but the brush does not, and they can still conduct electricity because they're in contact. الكرنت لو خارج من هنا بيعدي في الإيه؟ في الرينج. Okay? لا, you don't have to use your right. لا, هنا right hand برضو. All of this is the generator. All of this is the generator generating electricity. So it's right hand. Left hand, عشان بس في ناس هتفتكر left hand دلوقتي. Left hand إذا سمحتوا في الموتور. هيبقى في فرق ما بين موتور وإيه؟ وجنريتور كمان شوية. طب. The very last application is something we use every day. أنا قبل الحصة اكتشفت إن my phone is not charged. أنا ما شحنتش الإيه؟ التليفون خالص. خلاص؟ So I put it in my charger. رميتها في الشارجر بتاعي. What's the function of a charger? My phone's charger. Two things. إنها بتحول لي ال AC ل DC عشان جواها diodes, because my phone needs to work with a DC supply مش AC. And second, it decreases the voltage من 220 volts بتاعت المين supply اللي احنا قلناها to 5 volts اللي الموبايل محتاجها. My phone needs 5 volts. مين اللي بيعمل بقى ال decrease دي؟ A transformer. What does it do? It can decrease or increase ال EMF of a source. ازاي بقى؟ مفيش resistors بقى والكلام ده كله. How does it work? You have 3 components to the transformer. The first component is a coil. نجيب a primary coil, just a coil كده, and it's out. And then we have a secondary coil. So a second coil. من هنا رايح P means primary, S means secondary. and we turn these coils around what we call an iron core, just a piece of iron that's connecting the two sides together. Step by step, here's what happens. Step one, we connect this to an AC supply. ففي voltage بيدخل على AC supply, الcurrent بيدخل في الcoil, and when a current passes through the coil, ده بيgenerate a magnetic field أو produce a magnetic field. فthen a magnetic field is produced. الفكرة بقى إن because of the iron core and because of the shape of the iron core, the magnetic field is trapped. So step two, the magnetic field passes through the iron core. غصب عنه, because it has no other choice. It magnetizes the iron core and goes through it. فبيقعد يعدي في iron core. Because this magnetic field is moving and alternating, ليه alternating? عشان the supply is alternating. So the field itself is alternating. It cuts through the secondary coil, which generates an output voltage. V output. AC برضه. Sorry, mic away. Now, you might be thinking, ايه ده يا مستر؟ استفدت انا ايه؟ يعني انا عملت ايه طيب بالحركة دي؟ What use did I get? برافو يا مستر. خدت electricity, خدت a current or a voltage, you turned it to a magnetic field. So you produce a magnetic field, and then you use the magnetic field to generate electricity again. عملت electromagnetic induction, generate electricity again. برافو. أنا استفدت إيه؟ Well, I'll remind you of one thing في generating electricity part. Didn't we say we can increase the voltage induced by increasing the number of turns? هتقولي you can. طب if I have the primary and the secondary coil قصاد بعض, if the number of turns اللي في secondary coil أكتر من primary, you've got more turns هنا في secondary عن primary, what will happen to the voltage that you generate? According to induction, if you increase the number of turns of the coil, the voltage will increase. The voltage will increase. هتقولي صح, you're right, صح, الvoltage فعلا هيزيد. If you بقى, the opposite applies. If the number of turns of that secondary coil is less than the primary coil, قللنا number of turns, the voltage that you generate هنا will decrease. And maybe that's what I want. في الcharger بتاعي, I want to decrease the voltage. فبنروح حاطين two coils قصاد بعض. The primary coil has more turns than the secondary, so the voltage decreases, and we call this a step down transformer. Step down transformer. بتقل, بتنزل. Whereas if you increase the current, the voltage, I'm sorry, you step up the voltage. This is called a step up transformer. So what's a step up transformer? It's a transformer where the number of turns في secondary أكتر من primary, so the voltage increases. A step down transformer is when the number of turns اللي في secondary أقل من primary. My primary has more, this has less. So the voltage decreases. And both have their applications. احنا بنستخدم step down transformer every day in your chargers, in your computer, in your television, like almost all devices and electronics جواها step down transformer. Okay, step up هنشوفها بعد شوية. بس how do we calculate that voltage? وبتقل وبتزيد بقد إيه؟ It depends on the number of turns. The ratio of the number of turns, N is the number of turns, and P means primary. V is the voltage, and S is secondary. For the ratio of the primary and secondary voltage, هي الراتيو بتاعت the number of turns, primary على secondary. So for example, لو البرايمري هنا has 10 turns أو 10 loops, والسكندري هنا عنده 20 turns, like double, هي طبعا أكتر من double في الرسمة, but just double the number of loops. لو input voltage, the input voltage is 50 volts, output هيبقى كام؟ 100. if the number of turns doubles, the voltage also doubles. نفس الفكرة هنا. If the number of turns decreases, the voltage will decrease with the same ratio. ممكن بقى يطق في دماغك سؤال مهم جدا. ايه السؤال المهم جدا ده؟ طب مستر you stepped up the voltage. الفولتج زاد and we've created energy out of nothing. أقول لك لا. We don't create voltage out of nothing. بنزود الفولتج على حساب الكرنت. The voltage increases بس the current decreases. ايه ده ليه؟ Because according to the law of conservation of energy, energy cannot be created or destroyed. It can only be changed from one form to another. Which also means in the power input to the primary coil هي الباور output. الباور input هي الباور output. يا مستر مش الباور equals VI؟ أقول لك أو IV؟ أقول لك فده معناها إيه؟ إن ال IV it's not from heat energy. لا it's not from heat. إن ال current times voltage بتوع ال primary equals ال current times ال voltage بتوع ال secondary multiplied by each other. It's the same power. بس if you increase the voltage ال current لازم تقل to keep the same value. خلاص؟ Yes it's 4.6 يا عبد الرحمن. To keep the same value. Right? So you increase the voltage and the current بتقل مكانها. Mentally and visually, this is what I want you to imagine. Here's a 50 volt زي ما قلنا بقى. The primary coil here has 50 volts. The secondary has 100. Voltage زاد. برافو عليا. بس if the current here is 2 ampere, الcurrent هنا هيبقى 1 ampere. هتقل by half. هتقل بنفس الريشيو برضو. This is because 50 times 2 is 100 watts. هنا 100 times 1 اللي هي 100 volts times 1 ampere is also 100 watts. يعني كان عندي 2 amperes كل واحدة شايلة 50 volts. فthe total power is 100. هنا I only have 1 ampere, 1 charge. بس that 1 charge is now carrying the 100. The total energy is still the same. It's just لما الفولتج بتزيد الكرنت بتقل. ولما الفولتج تقل الكرنت تزيد. And this is only in a transformer لو سمحتوا. وبنستخدم الرول دي لو سمحت. بنقول IV equals IV. IV input equals IV output. أو IV primary equals IV secondary. Which begs the question. ليه يا مستر أصلا بنعمل step up؟ ليه نزود الفولتج؟ Why would you increase the voltage؟ علشان الإلكتريك cables دي. When we generate electricity in a power station, ونطلع electricity, this electricity has to travel like 5, 6, 800, maybe 1,000 kilometers sometimes. The longer these cables are, the higher their resistance, and the more energy is lost in them as heat. The more energy is going to be lost in the cables as heat. فتخيلوا كده. I generated electricity in the power station. طلعتها على الكيبل. It kept traveling 100, 200, 300, 400, 500, 700, 800 kilometers, and then it finally reaches my house. But oops, because it traveled 800 kilometers, you've lost 50% of your energy as heat. That is bad. I don't want that. طب how do I reduce the power lost in the cables بقى? You need to understand إن الكيبلز بتسخن because of two things. The power loss in the cables, which results as heat, depends on two things. One, it depends on the resistance of the wire. فكل ما الواير تبقى أرفع, thinner the wire is, the more energy it can lose as heat. فطبعا we make it thicker. طبعا زهرة بتقول and the length. The length is correct, but you know what? انت غصب عنك length 800 kilometers because you can't control that. The power station is in one place, your city is in another. Okay, I have a fixed length غصب عني. You know what? I'm forced to put 800 kilometers, if not more, of wire. So there has to be another way to reduce the heat lost, and that's through the current. كل ما الكرنت تقل, the heat lost in the cable بتقل. وخدوا بالكم بقى, decreasing the current is much more effective than decreasing the resistance. ليه? Power lost in a cable بتتحسب ب I squared times R. That's one of the formulas of A power if you remember. بس خدوا بالكم ان the I is squared, فده معناها ايه؟ If you decrease the current by half, I squared, squaring معناها even the half gets squared. فتبقى I squared over 4. The power lost does not decrease by half when you have the current. The power lost decreases by 4, by a quarter. Imagine بقى if I decrease the current 10 times. عملت step up 10 times the voltage, the current decreases 10 times. The power lost هتقل by 10 squared, which is 100 times. It is so much more effective to decrease the power lost by decreasing the current. وبقول لكم ايه, the transformer does it for free. انت ايه, عايز تزود الفولتج from 20,000 volt to 120,000 volts, الكرنت هيقل by that same amount. Did you increase the voltage 5 times, 10 times? الكرنت يقل خلاص 25 times. الكرنت هيقل 5 times, فالباور lost يقل 25 times. بس طبعا I cannot supply your house with 132,000 volts. فبنعمل ايه? Right before your homes بيبقى فيه transformer stations تانية. But this time دول مش بيعملوا step up, they step down. They step down قبل ما نوصل البيت. Yes. Very good. Let's solve a few questions. الأول على induction. A wire is moved down in a direction perpendicular to the magnetic field. So you're moving down. 3 changes are suggested. تعال نقراهم. The speed of the movement of the wire is increased. Okay. The magnetic field is decreased. Okay. Okay. Which changes increase the EMF induced? يعني ايه ال changes اللي increase the voltage? وقال لي the direction of the field is reversed. Increasing the speed صح, increase the voltage. Decreasing the magnetic field strength مش increase, decrease. The direction is reversed, والله ما فرقت. The direction changes the direction of the voltage or the EMF. It does not increase the value. فدي ملهاش لازمة برضه. So the answer is 1, B. Okay. The transformer will increase the voltage and decrease the current. الاتنين يا زهراء. ثانية واحدة بس, I'm going to pause for a second. There's a question here. In the transformer, when you step up, the voltage increases. خلينا أمسح بقى كل الشخبطة دي. In a transformer, when you step up, the voltage increases and the current decreases في نفس الوقت. And when you step down, the voltage decreases and the current increases في نفس الوقت. Because it cannot create energy to step up, it cannot destroy energy to step down. Energy is the voltage. Okay. Very good. نرجع بقى للquestions بتاعتنا. You're welcome. يلا, next question. A wire is moved across a magnetic field. This causes an induced current. ماشي, he generated electricity, induction. The induced current interacts with the magnetic field to produce a force on the wire. خدوا بالكم من language. The current applies a force on the wire. ثانية واحدة. Aren't you the one moving the wire مثلا down? What's the wire going to do? It's going to resist you. If you're moving the wire down, the wire will produce a force up to resist you. So what is the direction of this force? دي كانت Lenz's law. يلا. In the direction of the current? لا. In the direction of motion of the wire? لا. Opposite direction of the current? لا. It's opposite the direction of motion of the wire. If you move the wire down, the force is up. If you move the wire up, the force is down. So D is your correct answer. Next, here's a transformer question. 100% efficient. Sir, why is it not C? تاني هو مش بيسألك what's the direction of the current that's induced ولا حاجة. هو بيسألك what's the direction of the force that is going to act on the wire because of the induced current. مش احنا قلنا في Lenz's law the current is induced to oppose the change causing it. If you are moving the wire down, the wire is going to try to resist you. احنا قلنا it's toxic. You're trying to go down, هي هتgo ايه؟ up. This is the wire trying to go up. ايه ده؟ You move the wire up, the wire will try to apply a force ايه؟ down. You're moving the magnet towards it, it tries to repel you. You're moving the magnet away from it, it tries to attract you. But the force is always opposite to the change causing it, يعني to the motion of the object causing it. So if you're the one moving the wire down, the wire is going to apply an upward force opposite to your motion, not to the motion of the current, to your motion. Okay? Okay. A 100% efficient step-down transformer has a primary voltage VP and a primary current IP. Which row compares the secondary voltage and the secondary current؟ سمعت هو قال step down. Step down معناها the voltage بتاعت السكندري بتقل and the current في السكندري بتزيد يعني because the voltage decreases the current increases. فبيسألني what's the secondary voltage like? It's less, it decreases. What's the secondary current like? It's increased. So see. ده عشان قال لي step down. طيب what if it was step up? Let's fool around for a bit. What if I in blue say this is a step up transformer? هيبقى الانسر ايه بقى؟ the secondary voltage هتبقى greater. Secondary voltage هتبقى greater. And the secondary current هتقل. This would have worked if it was step up. It'll be the opposite. هتبقى B في الحالة دي. Okay? Now, let's take a short break. So, now let's talk or solve a couple of questions on electromagnetic induction, generating electricity. Okay, first, figure 6.1 shows two bar magnets. On figure 6.1, sketch the pattern and direction of the magnetic field between the bar magnets. فهنروح رسمين ايه بقى؟ Preferably with your ruler, بس draw a few straight lines. That's not straight enough بالنسبة لي. So I'm just going to use my ruler to draw a few straight lines from north to south, parallel to each other. Try to keep them equidistant. They don't have to be perfect, يعني, but try to. Put arrows on them from north to south. Now, next, figure 6.2 shows the same bar magnets with a coil of wire between them, and there's a handle, and he's rotating it كده, and there's a galvanometer. Please remember that the galvanometer is nothing more than a voltmeter or an ammeter. Like, it just measures voltage and shows you the direction of the current. Okay, there's nothing special about it. It's just a meter برضه. Name the parts labeled A. دول اسمهم A. These are called slip rings. Okay, next. The coil of wire is rotated in the direction shown in figure 6.2. Draw an arrow to show the direction of the current in the coil. Explain your answer. Type. What is the direction of the current in the coil? Here's where we start using the right hand rule. Hold on for a second. The magnetic field is from north to south. And this end of the wire is going to go up. Okay, this is not the answer yet. أنا بشرح بس كده. This is the direction of the force. So what's the direction of the current? The magnetic field is from north to south. If the force is upwards, the current is into or towards the page. The current will move this way. عايزين ترسموا الباقي. He only wants one arrow. Just draw any of these arrows. So current goes in or out of this direction. أنا مش محتاج red line ده. Oops, red line هيمسح كله. Eraser هيمسح كله. It doesn't matter. And that's the direction of the current. Just draw one of them. But then he says, explain your answer. So how are we going to explain this? Like, how are we going to explain our answer? Why did we choose this? What do you think I should do? Hey, Fleming's right hand a rule. Fleming's right hand rule. Or us, you can simply say, بس لازم نقول بقى ايه. If you're going to say something like, I used Fleming's right hand rule, then you need to mention the directions that you used. Like, we used Fleming's right hand rule, the magnetic field was to the right, and the direction of motion was upwards on this end of the wire. So the current was into the page. Like, it's like you're explaining how did you use the rule. Don't just say, I used Fleming's. لا, don't. Just say, using Fleming's right hand rule. I'm sorry, مش left, right hand rule with the magnetic field from north to south and the motion or the force is upwards. So the current upwards, عشان نبقى specific, on the left side of the pole. So just tell him where you applied the right hand A rule. Like, I took this side, the magnetic field was from north to south, it was moving upwards, so the current was in. He already sees the direction it was in. Okay? Yeah. Explain how rotating the coil continuously causes the galvanometer needle to show an alternating current. So as the coil is rotating, what does this do? It cuts the magnetic field lines, which does what? Which induces an EMF or a voltage. So the current goes to the, so it's 4 marks. I have to find something to say. Okay. So the current goes through the slip rings and brushes to the galvanometer. طب why is it alternating? هنقول because the coil's direction keeps changing every half cycle. يعني it goes up and then goes down. Goes up and then goes down. So the coil, or as the coil rotates, it cuts through the magnetic field. So it rotates, cuts through a magnetic field, inducing an EMF in the coil. But then what happens? A current, or the current, flows through the slip rings and brushes to the galvanometer. وfinally, عشان كده it moves. And finally هنقول له the current is alternating because the direction of motion of the coil, ممكن نقول because the coil is rotating and the direction of cutting the field changes every half rotation. 180 degrees. The first point, Yasif, is literally the definition of electromagnetic induction. As the coil rotates, what does it do? It cuts through the magnetic field of the magnet, which generates a current. This is from March 22, paper 4. Okay. Okay, next. Next one is from June 23, paper 4. We've solved a generator question and a few induction questions. Now let's solve a transformer question. The electricity supplied to a town is transmitted using a high voltage cable. A transformer in the town has a soft iron core. Let's make the handwriting bigger. This font size bigger. A transformer in the town has a soft iron core. Explain the principle of operation of a simple iron cored transformer. يلا. So simply put, هنقول ايه? Very long story. هنقول the AC or alternating voltage input to the primary coil produces an alternating or changing magnetic field. The field magnetizes the iron core, if a transformer, and cuts through or changes through the secondary coil. This induces an alternating voltage across the secondary coil. وشكرا. We just want the principle, صح? He doesn't want, is it step up or down or whatever. It's just, hey, how does it work? So the answer is almost always, the same, which is a voltage into the primary coil makes a magnetic field. The magnetic field magnetizes the iron core. The magnetic field cuts through the secondary coil. When it cuts through the secondary coil, this generates an output voltage, which is also alternating. The transformer steps the supply voltage down, let's assess down, from 220,000 to 33,000. فأنا معايا كده V primary and V secondary. There are 450 turns on the secondary. معايا N secondary. Calculate the number of turns on the primary coil. فيلا. VP over VS equals NP over NS. What's VP? 220,000. What's VS? 33,000. Equals 1 NP. What's NP? I don't know. What's NS? 450. Make NP the subject, and it's equal to 220,000 times 450 over 33,000. Calculator time. 450. Oops. Over. It's 3,000. Next. The electrical power transferred to the transformer by the high voltage cable is 77 megawatts. We haven't seen mega in a bit, but 77 mega means times 10 to the power of 6 or times 1 million. What? Calculate the current in the primary coil. نجيب الكرنت ازاي؟ صح, Mr. Power is IV. I have power. And what's the voltage in the primary coil? 22,000. What's the current? I equals P over V. The only trick here is using the correct value of the power, like changing it from megawatts to watts. So 77 times 10 to the power of 6. As I write megavolts is the answer. No, you can't write megavolts. You can write mega ampere, but no. Be careful with what your unit is, because we're calculating the current. We're not calculating power again. So 77 million over 220,000. So 77 10 to the power of 6 over 220,000, which is 350 ampere. Yes, sir. This is megawatts. I don't know why you're saying 7.7. This is 77 megawatts. Mega means times 1 million. It doesn't show up often, but it has here. So I have to change it to watts so I can get the value of the answer in ampere, because the power must be in watts, the current must be in ampere, the voltage must be in volts. غصب عني. These are the values that I have to have in the units. Final question in this section. We haven't seen a question about the AC yet, like supply, in terms of what position is correct. The diagram shows an AC generator. The graph shows the potential difference between the points X, Y, plotted against time. So it's just voltage over time. Which diagram shows the position of the coil? P. What's P? Oh, P is a maximum. This is not a minimum. This is a maximum. This is positive and negative, positive and negative. But if this is, for example, 220 volts, this is also negative 220 volts. It's a maximum. And when do you get the maximum voltage? When the coil is what? When the coil is horizontal. When the coil is horizontal, right? That's what you get. Oh, wait, sir. What the hell is this? How we have two horizontal answers. Which one do I choose? I'm confused. I'm confused. What do you guys think? It's rotating clockwise. It says a positive value of the potential difference indicates that X is more positive than Y. Oh. Thank you, Rana. Somebody's not. Thank you, Rana. What's different? Look at this. This is how terrifying some of these questions can be. Like, it's such an unassuming question, but look at this. These are different. The inside of the slip rings is different, which means this is 180 degrees different than this. It's finished one half of a rotation. So what we need to identify is, hey, is the diagram in front of me positive at X or negative? Because if it's positive, because if X is positive in this diagram, then I want the opposite diagram, A. If this is negative, then I want the opposite diagram. Like, if it's negative, sorry, I want the same diagram, C. So I have to go back. And what do I use? Fleming's right-hand rule. So again, what's this? If this is going to go upwards, just like we've done before, north to south, the current is going into. So the current is going to go this way, this way, this way, this way. Into this, passes here, out of that. So which side is positive and which side is negative in this diagram? Knowing that the current always flows from negative to positive. I'm going to erase this bit. In this diagram, where is the positive, where is negative? Is Y positive or X positive? Look at the current. Look at the current. If it's moving from Y to X, this means Y is a positive, X is negative in this diagram. In this diagram, Y is positive, X is negative. Because it's moving from Y to X. So, Mr. He wants point P, which is also negative. So what am I looking for? The opposite of this coil or the same coil if I still want it negative? The same coil. C is my answer. Why do you think I kept this till the very end? It's one heck of a question. I love it. But it's so annoying. You know those... I don't think you guys use magazines a lot, but when we used to buy comics and magazines, they'd have these games that you can play. You have these games you could play where you had to pick out the differences between the diagrams. And go like, oh yeah, I see an apple here, but not here. This is one of those skills that you kind of need to have, like being able to see differences. So you're still confused. Absolutely, no problem. Let's do this in reverse. Why is the answer C? Because he wants us to choose a position where the voltage is negative. Are you okay with this so far? He wants P, and P is negative. So what we want to know is the diagram that he's given me right now, is X negative or positive? Because he said in this sentence, a positive value of PD indicates that X is positive than negative, than Y, I mean. Which means if the value is positive, X is positive, Y is negative. So obviously, if the value is negative, X is negative, Y is positive. The idea is I need to find out, in this diagram, is Y positive or negative? Is X negative or positive? So what do? Use Fleming's right-hand rule here. Well, north to south. You know this is rotating clockwise. So you know this is moving upwards. The force on it is upwards. So Fleming's right-hand rule will point like this. This is your middle finger. This is your index finger. So this is the magnetic field. This is the direction of motion. This is the force. So the current is into the page. So in this branch of the coil, the current is into the page. مجرد ما تعرفي the current in one branch of the coil تعملي ايه؟ just draw it بقى. فدي هيمشي كده، ده هيمشي كده، ده هيمشي كده، ده هيمشي كده. We'll see it goes into this, out of this brush, to this ring, because that's the ring we're touching. And it moves from Y to X. Since the current always moves from positive to negative, يبقى which side is positive? ال Y ولا ال X? Y is positive, X is negative. فدي معناها this diagram right here where زي ما انتي خدتي بالك اهو, you're the one who pointed it out, ان ال inside of the slip rings هما في الدايركشنز دي, يعني اللي فوق هي اللي واصلة يمين واللي تحت هي واصلة شمال. I want to choose the same thing. ليه؟ Because he wants me to choose a diagram where P is negative, X is negative. And this is the same diagram. And if the diagram اللي فوق it was negative, so I just want the same diagram. I still want it negative. اتفقنا? Do you get it? It's a terrible question. It's a terrible question. Poor June 2023 students who faced this and probably were like, what's the difference? They all look the same. It is 1 mark. وزي ما اتفقنا, when it comes to, and we'll talk about this when we talk about past papers again in the future, inshallah. يعني next week ولما نخلص بقى الريفيجن كله, we're going to start solving past papers, and I'll like just have a single session where we only talk about how to solve past papers, how to manage your time, and that includes giving up on questions. لف ودوران مش طبيعي بالظبط كده. يلا, very last chapter, very small one. The force on a current carrying conductor. This is the opposite of induction. يعني ايه? In induction, we move the coil, it generates electricity. هنا العكس. هنا we will give it electricity and it gives us kinetic energy. It gives us a force. How does it work? Here's how it basically works. How do you demonstrate this effect? You connect a battery to a wire. So when there is a current that flows through the wire because of your battery, we're not moving it, you pass a current through the wire. ايه اللي هيحصل step by step؟ بص بقى. What happens is this. The current that flows through this wire produces a magnetic field. Current that flows through the wire produces a magnetic field. This magnetic field interacts with the field from the bar magnet. So you have how many fields in this space? 2. The 2 fields overlap and interact. So what do? They apply a force on the wire because magnetic forces always appear or like are produced because of when two fields interact. North pole and North pole, their fields repel each other, they apply a force. فهنا is the same thing. The field of that single current and the field of the magnet interact, so they apply a force on the wire. So how do you explain the demonstration? It's very simple. Put a wire between the poles of a magnet, connect the wire to a supply. You will find that the wire moves up or down, move perpendicular to the field. How do we find the direction of the force? زي ما كان في Fleming's right hand rule الجنريتور أو الإندكشن. هنا we have Fleming's left hand rule. It's the exact same rule but with your left hand. So if you apply it to this diagram, هنا I was very fancy بقى. عارفين رحت دخلت في فوتوشوب بقى وعملت بقى PNG و transparent background ورميتها في I was very happy with myself وأنا بعمل الحركات الصعبة دي. So if you take your left hand and you put it on top of this diagram, from north to south is your index finger. So from north to south. The current is out of the page, or زي ما قلنا قبل كده, it's moving from A to B. دي اللي given, like we have the field, we have the current. خلاص, this is given, and this is given. What do we want to find? The force. But the magnetic field is from north to south, the current is towards me, the force is upwards. So this wire is going to go up. And that's how you use the left-hand rule. Now I can change whatever it is you want, but so that's how you use the left-hand rule. But I need to point something out. Sometimes هنرسم diagrams زي دي. This is where my fancy Photoshop skills ended. Instead of showing you where the North Pole and the South Pole are, I can just draw a space كده وأقول لك this magnetic field is into the page. What this physically means is that إن أنت خدت الwire, the paper, and you have a magnet in front of the paper, the North Pole of the magnet in front of the paper, and the South Pole of that magnet behind the paper. So now the magnetic field is moving from north to south, but it's going into your paper. And this is what into the paper means. Okay, so the magnet is above the paper and behind them and below. So by left-hand rule, you point into the page. You're pointing into the page because I said the field is into the page. If the current is moving to the right, the current, the force that you have, which is your thumb, is upwards. Well, look at what's the flow of charge, current? It's the flow of positive charges. Keep this in mind عشان لما هنيجي نحل مسألة على direction and left hand rule, we're going to change the direction a bit, okay? Very good. Next, we can use this effect, which is the force on a current carrying conductor, to build a DC motor, which is a device that does what? That takes in electricity and rotates. Exactly like a generator. Look at the design. You have a coil, والcoil محطوط فين? Between the poles of a magnet. It's pivoted in the center. But this time مش إحنا اللي بنعمل rotation. We provide the current. إحنا اللي بندخل current. So when the current flows from positive to negative into the coil, خلاص, the magnetic field is from north to south. هنا the current is into the page. فالforce لتحت. Because بقى you have a coil with two forces on it, واحدة من الناحية دي وواحدة من الناحية دي, and a pivot in the middle, this experiences a moment. A turning effect. It experiences a moment. فبتلف. So because you have two forces on either side of the coil, again, واحدة لفوق واحدة لتحت, this experiences a moment and it rotates. A rotation ده بيعمل ايه? Moment. But here's the thing. there's a small difference ما بين الجنريتور والموتور. First, الموتور فيه battery أو supply. Second, we still have carbon brushes for the same reason, to conduct electricity to the coil without breaking the wires. عشان ال external circuit ما تتقطعش وال internal circuit أو ال internal coil ده يلف براحته. However, في حاجة زيادة. Why is this ring cut in half? What is this split ring? يعني إيه ال split ring? Now, you just need to memorize the function, even though I'll show you what it means. The function of the split ring is to reverse the current every 180 degrees. Like every half a rotation, it reverses the current. Why? To keep the coil rotating in the same direction. عشان يفضل الكويل rotate. Without it, the coil will stop. أنا مش فاهم قصدك إيه مستر? What does that have to do with anything? Let me بقى show you a quick video. Now, to those of you who were with me in school, it's the exact same video, but we're going to draw on top of it بقى. Yeah. You can find this on YouTube. Here's a coil. This is a coil. Where's my annotation tool? Here's the coil. Okay. And here's the magnet. Magnetic fields from north to south. And here's the battery. Here's the positive, here's the negative. So the current is going to flow كده, 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 and into this side. هيلف and out of this side. Goes out. So if I apply Fleming's left-hand rule, because this is the motor بقى مش الجنريتور, huh? If you apply Fleming's left-hand rule, كده, from north to south, and this current is into the wire, كده اهو, this is the current into the wire, your thumb will point upwards. For this side is going to go up, the other side is going to go down. And if I click play, this is what happens. It rotates clockwise زي ما شفت. So let me delete بس drawing بتاعتي. I'm going to draw again. So it rotates clockwise. Stop. Here's the thing. زي ما قلنا, this side is going up, this side is going down. محدش معترض. Everybody agrees. But if it keeps going up, 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 stop. Eventually, when it reaches this point فوق هنا, اللي بيgo up ده ما ينفعش go up anymore. It has to start going down. And the other side that's going down can't go down anymore. It needs to start going up. In order for the force that you apply, in order for this force to change direction, you either change the poles, مش هتحصل, or you change the poles of the battery, also مش هيحصل. So instead, what does this for you, what changes the current direction automatically for you, is the slip ring. فأول ما بتوصل للvertical position ده, it changes the direction of the current. عشان اللي فوق ده ينزل لتحت, عشان اللي طالع لفوق ده ينزل لتحت, واللي تحت ده يطلع لإيه؟ لفوق. And I'm going to play and pause again, just a second. Stop right here. Do you see what's happened? Here's what happened. Let's call this side A. Let's call this side B, and wire B. Wire B's half of the ring is touching the negative brush, and wire A's half of the ring is touching the positive brush. هتقولي ماشي يا مستر وبعدين. If you click play بقى and you watch what's going on, do you see what's going to happen بعد شوية? A is up here, it's still touching the positive. Still touching the positive, because it's still going up. ال A جت من هنا لهنا, And now the side of A is touching what? The negative. And the other side, which was B, that has gone to the other side, تحت هنا, B is now touching which brush? The positive. But this automatically does the change for you. البرش الكويل وهو بيلف والرينج وهو بيلف automatically بيعكس الايه؟ الcurrent for you. Every half rotation or every half cycle. It alternates automatically, but it is not an alternating current, okay? The current from the source is still DC. Has a positive and negative side. هو بس الرينج ده وهو بيلف it keeps touching the opposite sides of the brush. كل نص لف. Okay? How do we generate more voltage? That's easy. Sorry, how do we make it spin faster? We're not generating here. We're making it spin faster. That's easy. You increase the voltage or the current. Or you increase the number of turns. You increase the number of coils. Or you use a stronger magnet. Finally, بقى. This is an extra point من عندي because a few exams like to use this concept, which is what بقى. If you have two wires next to each other, each wire that has a current flowing through it produces a magnetic field. لو المagnetic field بتاعت الواير دي عدت على wire تانية also that has a current, it will experience a force. برضو Fleming's left-hand rule. Okay? So the magnetic field that cuts through this wire applies a force on wire B. A applies a force on B. ومش بس كده كمان ما تنسوش ان B also produces a magnetic field. B also produces a magnetic field. B applies a force on A using برضه Fleming's left-hand rule. Okay? Turns out بقى these forces are always opposite in direction. But if the currents are in the same direction and you apply Fleming's left-hand rule correctly, we're taking just the shortcut here. A is going to move to the right, B is going to move to the left. It's as if they will attract each other. Whereas if you reverse the direction of the currents, they're both in opposite directions, they will move away from each other. And try this out on one of these diagrams. يعني تعالوا نجربها في الdiagram دي. Like, let's try this out here. I want to try the force of B on A عشان أنا هنا رسم المagnetic field of B. Look at the direction of the magnetic field. Okay, it's going to rotate clockwise, 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 and this is it. Right now, this magnetic field is out of the page. إنها جاية towards me. The current in this wire is upwards. Well, left-hand rule, towards me, current is upwards, يعني كده. Current, magnetic field is towards me. It's very hard to do in the air كده. Current is upwards. So Fleming's left-hand rule, magnetic field, current is upwards. You will experience a force فين? To the left. And this will experience a force to the right. Actually, أنا آسف, there's a small mistake in this diagram. I should try to fix this in the source. دي المفروض تبقى كده. I don't know why the arrows are so long. It's supposed to be clockwise, the right-hand rule. Let's repeat this again. Something's wrong with the diagram. The current in B is downwards. But the magnetic field direction is now going to be clockwise. So it's into the magnetic field, sorry, is into the page. The current is up, so the force is to the A, is to the left. Do this again, but on the other side, the force is to the right. All in all, if you have two wires next to each other, the magnetic field of one wire will apply a force on the other. يعني واحدة المagnetic field بتاعتها هتعمل force على الواير التانية، والواير التانية هتعمل force على ايه؟ أولانية. If they're in the same direction, they attract. If they're in opposite directions, the currents, that is, they will repel. Best. Let's solve a few quick questions كده. And this is بقى the thing that I wanted to point out. لما احنا بنعمل Fleming's left hand rule, the middle finger is the current. Your middle finger is your current. And current is the flow of positive charges. خدوا بالكم. An electron, which is negative, moves into a uniform magnetic field. The arrow shows the initial direction of motion of the electron. The direction of the magnetic field is into the page. لازم يقول لي it's in which direction does a force act on the electron when it enters the magnetic field? فيلا. Fleming's left-hand rule, it's into the page. The motion is to the right. For the force is upwards. لا. It's downwards. ليه? Because according to this rule, if a positive charge or current is moving to the right, it will move up. بس هنا the electron is negative, so it will always move opposite to the direction of the rule. So it goes down towards the bottom of the page. So please خدوا بالكم, is he talking about an electron which is negative or a positive charge or a current? ماشي? Next. Figure 8.1 shows a horizontal flat coil in a magnetic field. The coil is connected to a cell. The coil rotates. Determine the direction of movement of the side AB, this side over here, relative to the plane of the coil. Will it move up or down? يلا, Fleming's left-hand rule. بس أنا إيش عرفني current فين? The cell, the long side of the cell is positive, the short side of the cell is negative. So the current is moving this way, from positive to negative. Fleming's left-hand rule, north to south, the current is لا, try this again. North to south, the left hand, not right. The current is into the page, so the force here is downwards. Force here is down the page or downwards. Explain how you determined the direction in A. Using, I think we've done this last time, بس with the right hand rule فوق في generator, this time it's the left hand view. Using Fleming's left hand rule with the magnetic field from north to south, and the current is into the page. So the force is downwards, but so we're just explaining how we determined it. So mentioning Fleming's left-hand rule is a mark, and telling him what the directions of the north and south and what the direction of the current is. Oh, north to south will current into. ليه? Because دي positive ودي negative. Let me zoom in. دي positive ودي negative. فالكرنت هيمشي ازاي كده؟ لو ده north to south والcurrent is into, your middle finger بإيديك الشمال is pointing into, والindex finger لسه لازم يبوينت يمين، إيدك منظرها هيبقى عامل كده. خلاص؟ with your middle finger pointing كده. ده الcurrent into وده north to south. هيتبقى لك الفورس لتحت. ماشي؟ بالleft hand مش الرايت لو سمحت. left hand. طيب. State and explain what happens to the coil when it reaches a vertical position. أول ما بتريتش vertical position. Wait يا مستر ثانية واحدة. هو مش حاطط split ring صح؟ it will stall or get stuck in the vertical position because the direction of the forces on the coil will not reverse. Or ممكن نقول له because a force on AB is still upwards. So it will not rotate. بس هتقف ليه؟ الفورسز زي ما هي. The direction of the forces هتفضل زي ما هي, so it will not continue to rotate. To operate as a motor, a split ring commutator, that's the full name of the split ring commutator, and brushes are added. Explain the effects of the split ring commutator and the brushes. يلا هنقول الإفكت بتاعت both. Because the forces are parallel to the field, the forces are not parallel to the field. Rana, this is not a generator, huh? This is not a generator. It's not about generating electricity so you get 0 volts. احنا مدخلين current already. It's going to get stuck because we have not changed the direction of the current. We supply the current, not the other way around. Yeah. What are the effects of the split ring and the brushes? هنقول له they rotate or they change or reverse is the better term. The direction of the current every 180 degrees to keep the coil rotating in the same direction. وهزود عليها, even though you should have honestly added the line because it's 3 marks, they also conduct electricity or the current without breaking the wires of the external circuit or of the supply or of the cell or of the. But because he said 3 marks, I'm keeping myself safe by adding the function بتاع brushes كمان. Maybe it's not necessary, maybe it is. But you know what? I'm like you in an exam. I'm stressed out. What should I say? They're both physically correct terms. But you must, this is the most important part. You must talk about reversing the direction of the current every 180 degrees عشان يفضل الcoil rotating in the same direction. That must be added. Last questions, or a couple of questions. The diagram shows a wire hanging freely between the poles of a magnet. There's a current in the direction shown, down the page. The magnet and the current cause a force to act on the wire. What's the direction of the force? Yep. North to south يعني شمال. The current is down, my thumb is pointing كده. فدي كده يعني into the page, away from me. And then, which component forms part of a DC motor, but not a simple moving coil AC generator, يعني not the generator. اللي في الموتر بس مش في الجنريتر. Is there a coil? Yes, there is. Are there brushes? Yes, there are. Is there a magnet? Yes, there is. Is there a split ring commutator in a generator? No, there isn't. So that's my answer because I'm looking for what's not in a generator. Thank you very much.